Here's my question. Number one, if there is no physical barrier between the Earth's atmosphere and space, which there isn't, and I have sources here saying there isn't, and obviously it's intuitive. We all know that there isn't. My question is, how can you have a vacuum, space, attached to a non-vacuum, Earth, and still retain the properties of a vacuum and a non-vacuum in the same system simultaneously? Please give me your answer in the law of entropy context.
I didn't understand the last three words you said.
I said, please give me your answer in a law of entropy context.
Okay, I'm not terribly familiar with the law of entropy. I do know that I think entropy is always supposed to be increasing, which is entropy is disorder. But I'm not going to answer it like in the context of disorder order. But what I will say, first off, that's a great question. That's a really big stumbling point for a lot of people, is how can you have a vacuum next to a non-vacuum? And the other word that's going to cause people to burst into flames is gravity. So
okay.
the Earth's atmosphere is held on by gravity. And
okay.
What people don't realize is that the 15 pounds per square inch, or it's like 14.5 pounds per square inch, which is standard atmospheric pressure, which most people who are listening to this are experiencing. That's a weight per unit of area. So 15 pounds per square inch. So literally, if you had something that was 15 pounds and then you had it, resting on a postage stamp on your hand, you're like, wow, that's pushing down really hard. 15 pounds per square inch. Well, what that is the weight of a column of air, literally 1 inch by 1 inch, that is 60 miles tall.
Okay.
And obviously, it gets thinner as you go higher and higher and higher and higher. But what is
okay? So your answer is weight and gravity, correct?
The weight of the atmosphere, but the thing is, the gas is compressible. So the lower layers of the atmosphere, say the lower 5 miles of the atmosphere, is where what we call breathable atmosphere. I mean, you do have trouble, climbing Mount Everest. But then just a couple, miles further up, you can't breathe. There's these various lines. There's this Armstrong line where the liquid in your lungs boils off because the pressure's so low, and the air gets thinner and thinner and thinner and thinner, and then you have the carbon line.
This isn't answering my question though, Charles.
Okay. But
the law of entropy says basically, unless it is hindered purposely in nature, heat flows from hot to cold always. Energy concentrated to disperse always.
Yes.
High pressure, which you were talking about, is working against you here. High pressure to low pressure always.
Okay, but what was the first few words of that? It was something
unless it is purposely hindered in nature.
There you go. Purposely hindered.
That means unless there's a physical barrier.
No.
Your car what?
Purposefully hindered does not mean physical barrier.
Yeah, it does.
Well,
yes, it does. Yeah, it's like your car tire. When you press that valve in your car tire, what happens?
I'm sorry. The valve in a what? I couldn't
hear
you.
Tire in your car tire. High pressure to low pressure. What happens to the air when you press that valve?
Oh, a car tire. Right. So what you're talking about is on the surface of the Earth, where the air pressure is 14 pounds per square inch. If you have an area of high pressure and a physical barrier and an area of low pressure, yes, you release that valve, the air is going to go from high pressure to low pressure.
The barrier is the tire.
But the barrier is the tire and the barrier is the valve. Absolutely, that is a system. Okay, we call it a closed system.
I got you. I want you to show me an experiment where gravity or anything else overcomes entropy.
Well, but the thing is, the Earth's atmosphere is 60 miles thick. I mean, it gets so thin at the very top that it's only one molecule, or a handful of molecules per cubic meter. So, but the gravity is providing the pressure differential.
Okay, I just asked you. I said, please provide me the experiment that shows. Now you can source it. You don't have to know it exactly. I want to see the experiment where gravity overcomes the second law of thermodynamics.
Well, but the thing is, you're mixing apples and oranges. It's not overcoming the second law of thermodynamics.
It's
the
not.
second law of thermodynamics says unless otherwise encumbered so I forget the wording. Okay, and what's encumbering pressure is the layers of the atmosphere. So real quick example, you know about the Jenga, pile of blocks called Jenga, right?
Why are you giving me an analogy when we have the actual setup
because the analogy is, if you have this tower of blocks, of wooden blocks called Jenga, you're familiar with the toy, right?
I'm familiar with Jenga.
Okay, so it's very easy to pull the blocks out, to slide the blocks out near the top of the tower, because they're only supporting a few layers of tower. But at the very bottom of the tower, they're supporting their weight plus the weight of everything above them. That's what's happening in the atmosphere. The pressure in the atmosphere isn't just this magical pressure that came out of nowhere, like in a tire, pump up a tire. It's supporting the weight of the layers of atmosphere above it. So the pressure is going to decrease as you get higher up, just simply because it's resting upon layers and layers of atmosphere, just like the layers of the blocks of Jenga.
So what is it gravity, or is it weight? Well, which is the same as gravity, correct?
Yeah. So it's the question is self-referential.
Okay, gravity is a begging the question fallacy to begin with. I want you to show me an experiment that shows gravity overcoming entropy.
Gravity does not overcome entropy. That's the point.
You already said that, then that's your problem.
No, gravity does not overcome entropy.
That's right. I know it doesn't.
You do not have a system, and again, it was the first few words you said when you talked about the law of entropy. It was like, unless otherwise encumbered or artificially.
Unless it is hindered purposely.
There you go. And what's going to hinder it purposely is the Jenga-like blocks of atmosphere, where literally the upper layers of atmosphere are pushing down.
That's not a purpose hindering, sir. Purposely has intent. That means human intelligent involvement, intent. You're telling me that if I have a vacuum chamber and I put a separator or a barrier between the two, and in the other side of the chamber I have high pressure, you're telling me that if I pull that barrier away, that high pressure will not flow into that vacuum chamber?
Now, you know for a fact I never said any such thing. So
that's what you didn't say it, but that's what you're implying by your response.
What I'm saying is, across the 60 miles of atmosphere, you go from an area of high pressure to an area of low pressure, because it is the weight of the air. It is literally the weight of the air. So we have high pressure, which is 15 pounds per square inch at sea level, and we have low pressure, which is very, very close to zero at the Kármán line.
Hey, Robert, let me know if my screen's sharing.
Yeah, you should be good.
Are you looking at this, Charles?
Yes. Flat Earth proof, sea level, 760 torr. I guess a torr is a millimeter of mercury.
Look at these values here. We are talking about exponential values of pressure gradient.
Exponentially small.
Exponential. It doesn't matter how small. 10 to the 17th?
Yes.
For interstellar deep space, down to 10 to the negative 12th. That's exponential magnitudes of pressure gradient.
Okay. Well, no. It's
it is. It's looking at you right in the face.
And here's my clarification. Exponentially small means close to zero. So, for example, if I gave you the number 14 and a half,
it doesn't.
If I gave you the number 14 and a half, and I say I want you to go to outer space, what are you going to do using subtraction? You'd say I'm going to subtract 14 and a half.
Okay, let me go up here to my experiment. Hold on 1 second.
So, yes, there was a significant exponents, but it was exponentially small, which means a number that is 0.000000001, which is a very, very small number close to zero. But it's not a huge number. It's a small number. That's
okay. Let me do an experiment for you.
It's a vacuum. Close.
It's not. Let me do an experiment for you. Let's take an empty liter bottle of soda, suck the air out, and replace the cap quickly. Ensure the sides of the container are somewhat collapsed, denoting a minor vacuum. Pound a 3-inch nail through a small sheet of 1/4-inch plywood. Lay the board flat on the ground, butt it up against the strong gravity with the business side of the nail in the vertical position, puncture the bottom of the bottle with the nail, and tell us what happens. What happens?
It sucked the water up into the bottle.
It sucks the air right in. Now,
sucks the-
for my claim, flip the script, where you have an exponentially stronger vacuum and an exponentially weaker gravity. What do you suppose will happen?
But no, it's not exponentially stronger vacuum.
Yeah, it is, because it's lower. The density is so low. The pressure gradient is so high, in other words, between the two systems.
No. See, that's the misunderstanding. The pressure
It's not a
gradient
misunderstanding.
is
I
not high.
posted this to a physics professor at the University of Missouri, and he couldn't answer it.
Okay, but that's because it's got some false assumptions baked in.
It doesn't have any false assumptions. It's a law of entropy, for crying out loud.
No. When you said the phrase, the pressure differential was exponential, that is incorrect. The pressure differential.
Exponential magnitudes of pressure gradient.
No, that is absolutely false.
It's absolutely true. I just showed them to you.
Yeah, but what you were showing me was not just something that's exponential. The word exponential kind of triggers people to think really big numbers. The pressure gradient.
They are big numbers. The pressure gradient.
No, the you know what the big number is, John? The pressure gradient between the Earth's surface and outer space is 14.5. That is not
the pressure gradient between the Earth's surface
and say deep space.
8 torr to 10 to the negative 17th torr.
Yes. Now subtract those, and what do you get?
You subtract them.
Yes. That's a differential, right? How do you find a differential? You take it, initial minus final, or you could take final minus initial. The way you find a differential is you take two values and you subtract them. That's the differential. And what is the pressure differential between Earth's surface and outer space? It's 14.5. It's not exponential. It's simply 14.5.
All right, I'm gonna leave this. I want to see the experiment, sir. I want you to show gravity overcoming. This is entropy.
No, but gravity does not overcome entropy.
But you just
Entropy
said
is
it
the
before
law.
that it overcame it.
Entropy is the law. Gravity is not overcoming entropy. So please don't misunderstand me.